Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You need to set access to BigQuery for different departments within your company. Your solution should comply with the following requirements. Each department should have access only to their data. Each department will have one or more leads who need to be able to create and update tables and provide them to their team. Each department has data analysts who need to be able to query but not modify data. How should you set access to the data in BigQuery? The options are: Option A, create a dataset for each department. Assign the department leads the role of owner, and assign the data analysts the role of writer on their dataset. Option B, create a dataset for each department. Assign the department leads the role of writer, and assign the data analysts the role of reader on their dataset. Option C, create a table for each department. Assign the department leads the role of owner, and assign the data analysts the role of editor on the project the table is in. Option D, create a table for each department. Assign the department leads the role of editor, and assign the data analysts the role of viewer on the project the table is in.
To arrive at the correct answer, we focus on the keywords. Each department should have access only to their data, create and update tables, query but not modify data.
The correct answer is option B, create a dataset for each department. Assign the department leads the role of writer, and assign the data analysts the role of reader on their dataset.
Why is this correct? B. Creating datasets per department ensures data isolation. The writer role, roles/BigQuery.dataEditor, allows leads to create and update tables, while the reader role, roles/BigQuery.dataViewer, allows analysts to query without modifying data. Why are the others incorrect? A. Assigning data analysts the writer role would allow them to modify data, which directly violates the requirement that they must only query but not modify data. C. Assigning project-level owner and editor roles grants access to all datasets within the project, violating the requirement that departments should only access their own data. D. Assigning project-level editor and viewer roles grants access to all data across the entire project, which fails to isolate data access per department.
You operate a database that stores stock trades and an application that retrieves average stock price for a given company over an adjustable window of time. The data is stored in Cloud Bigtable, where the date time of the stock trade is the beginning of the row key. Your application has thousands of concurrent users, and you notice that performance is starting to degrade as more stocks are added. What should you do to improve the performance of your application? The options are: Option A, change the row key syntax in your Cloud Bigtable table to begin with the stock symbol. Option B, change the row key syntax in your Cloud Bigtable table to begin with a random number per second. Option C, change the data pipeline to use BigQuery for storing stock trades, and update your application. Option D, use Cloud Dataflow to write a summary of each day's stock trades to an Avro file on cloud storage. Update your application to read from cloud storage and Cloud Bigtable to compute the responses.
To arrive at the correct answer, we focus on the keywords. Retrieves average stock price for a given company, Cloud Bigtable, date time of the stock trade is the beginning of the row key, performance is starting to degrade, improve the performance.
The correct answer is option A, change the row key syntax in your Cloud Bigtable table to begin with the stock symbol.
Why is this correct? A. Changing the row key to begin with the stock symbol avoids hotspotting caused by sequential datetime keys. It also groups related data together, optimizing read performance since queries retrieve data for a specific company. Why are the others incorrect? B. While a random number prevents write hotspotting, it scatters data for a specific company across nodes. This makes read operations highly inefficient, as the application cannot perform contiguous scans to retrieve a company's data. C. BigQuery is optimized for analytical workloads and not suited for applications with thousands of concurrent users requiring low latency reads. Bigtable is the correct choice, but the row key design needs adjustment. D. This approach adds unnecessary architectural complexity and latency. Cloud Bigtable can easily handle the required performance for thousands of concurrent users if the row key schema is designed correctly to avoid hotspotting.
You are operating a cloud Dataflow streaming pipeline. The pipeline aggregates events from a cloud pub/sub subscription source within a window and syncs the resulting aggregation to a cloud storage bucket. The source has consistent throughput. You want to monitor and alert on behavior of the pipeline with Cloud Stackdriver to ensure that it is processing data. Which Stackdriver alerts should you create? The options are: Option A, an alert based on a decrease of subscription/number_undelivered_messages for the source and a rate of change increase of instance/storage/used_bytes for the destination. Option B, an alert based on an increase of subscription/number_undelivered_messages for the source and a rate of change decrease of instance/storage/used_bytes for the destination. Option C, an alert based on a decrease of instance/storage/used_bytes for the source and a rate of change increase of subscription/number_undelivered_messages for the destination. Option D, an alert based on an increase of instance/storage/used_bytes for the source and a rate of change decrease of subscription/number_undelivered_messages for the destination.
To arrive at the correct answer, we focus on the keywords: Cloud Dataflow Streaming Pipeline, Cloud Pub/Sub Subscription Source, Cloud Storage Bucket, Monitor and Alert. Ensure that it is processing data.
The correct answer is option B, an alert based on an increase of subscription/number_undelivered_messages for the source and a rate of change decrease of instance/storage/used_bytes for the destination.
Why is this correct? B. An increase in undelivered messages means the pipeline is failing to process incoming pub/sub events. A concurrent decrease in the rate of storage growth confirms that data is not reaching the cloud storage bucket, successfully alerting on stalled processing. Why are the others incorrect? A. A decrease in undelivered messages and an increase in storage bytes indicate healthy pipeline operation, which is the desired state and should not trigger an alert. C. This option incorrectly assigns storage metrics to the pub/sub source and message delivery metrics to the cloud storage destination. D. This option swaps the appropriate metrics, applying storage used bytes to the pub/sub source and undelivered messages to the cloud storage destination.
You currently have a single on-premises Kafka cluster in a data center in the US East region that is responsible for ingesting messages from IoT devices globally. Because large parts of globe have poor internet connectivity, messages sometimes batch at the edge, come in all at once, and cause a spike in load on your Kafka cluster. This is becoming difficult to manage and prohibitively expensive. What is the Google recommended cloud-native architecture for this scenario? The options are: Option A, Edge TPUs as sensor devices for storing and transmitting the messages. Option B, Cloud Dataflow connected to the Kafka cluster to scale the processing of incoming messages. Option C, an IoT gateway connected to Cloud Pub/Sub, with Cloud Dataflow to read and process the messages from Cloud Pub/Sub. Option D, a Kafka cluster virtualized on Compute Engine in US East with cloud load balancing to connect to the devices around the world.
To arrive at the correct answer, we focus on the keywords: ingesting messages from IoT devices globally, spike in load, cloud-native architecture.
The correct answer is option C, an IoT gateway connected to Cloud Pub/Sub, with Cloud Dataflow to read and process the messages from Cloud Pub/Sub.
Why is this correct? C. Cloud Pub/Sub is a fully managed, globally scalable messaging service that easily absorbs sudden load spikes from batched IoT messages, paired perfectly with Dataflow for processing. Why are the others incorrect? A. Edge TPUs are hardware accelerators meant for running machine learning inference at the edge, not for buffering or transmitting large volumes of batched messages. B. Keeping the Kafka cluster and only adding Dataflow fails to resolve the fundamental scaling and management challenges of the Kafka cluster itself during load spikes. D. Virtualizing Kafka on compute engine VMs requires manual cluster management and scaling, ignoring the benefits of fully managed, autoscaling cloud-native solutions like pub/sub.
You decided to use Cloud Data Store to ingest vehicle telemetry data in real time. You want to build a storage system that will account for the long-term data growth, while keeping the costs low. You also want to create snapshots of the data periodically, so that you can make a point-in-time, PIT, recovery, or clone a copy of the data for Cloud Data Store in a different environment. You want to archive these snapshots for a long time. Which two methods can accomplish this? Choose two. The options are: Option A, use managed export and store the data in a cloud storage bucket using nearline or coldline class. Option B, use managed export and then import to Cloud Data Store in a separate project under a unique namespace reserved for that export. Option C, use managed export and then import the data into a BigQuery table created just for that export and delete temporary export files. Option D, write an application that uses Cloud Data Store client libraries to read all the entities. Treat each entity as a BigQuery table row via BigQuery streaming insert. Assign an export timestamp for each export, and attach it as an extra column for each row. Make sure that the BigQuery table is partitioned using the export timestamp column. Option E, write an application that uses Cloud Data Store client libraries to read all the entities. Format the exported data into a JSON file. Apply compression before storing the data in cloud source repositories.
To arrive at the correct answer, we focus on the keywords: Cloud Data Store, long-term data growth, keeping the costs low, create snapshots of the data periodically, point-in-time, PIT, recovery, clone a copy of the data, archive these snapshots for a long time.
The correct answers are Option A, use managed export, and store the data in a cloud storage bucket using nearline or coldline class. And Option B, use managed export, and then import to Cloud Data Store in a separate project under a unique namespace reserved for that export.
Why is this correct? A. Cloud Data Store managed export creates snapshots stored in cloud storage. Using nearline or coldline effectively meets the requirement for low-cost, long-term archiving of these snapshots. B. Managed export allows you to create snapshots that can be easily imported into a separate project or namespace, fulfilling the requirement to clone data for a different environment. Why are the others incorrect? C. Deleting temporary export files prevents you from retaining data store snapshots for long-term archiving, and BigQuery is not designed for direct PIT recovery back to data store. D. Writing custom application code to stream entities to BigQuery is overly complex and does not create native data store snapshots required for PIT recovery or cloning. Why are the others incorrect? E. Cloud source repositories is designed for source code version control, not for storing or archiving large telemetry data backups or database snapshots.
You need to create a data pipeline that copies time series transaction data so that it can be queried from within BigQuery by your data science team for analysis. Every hour, thousands of transactions are updated with a new status. The size of the initial dataset is 1.5 PB, and it will grow by 3 terabytes per day. The data is heavily structured, and your data science team will build machine learning models based on this data. You want to maximize performance and usability for your data science team. Which two strategies should you adopt? Choose two. The options are: Option A, denormalize the data as much as possible. Option B, preserve the structure of the data as much as possible. Option C, use BigQuery update to further reduce the size of the dataset. Option D, develop a data pipeline where status updates are appended to BigQuery instead of updated. Option E, copy a daily snapshot of transaction data to cloud storage and store it as an Avro file. Use BigQuery's support for external data sources to query.
To arrive at the correct answer, we focus on the keywords, time series transaction data, queried from within BigQuery, updated with a new status, maximize performance and usability.
The correct answers are option A, denormalize the data as much as possible. And option D, develop a data pipeline where status updates are appended to BigQuery instead of updated.
Why is this correct? A. Denormalizing the data maximizes read performance in BigQuery by reducing the need for costly joins, making it ideal for analytical queries and machine learning models. D. BigQuery is optimized for append-only operations. Appending status updates rather than executing update statements is faster, more cost-effective, and ideal for tracking time series changes. Why are the others incorrect? B. Preserving a highly structured or normalized data format requires complex joins in BigQuery, which degrades both query performance and usability for data science tasks. C. BigQuery update operations are resource-intensive, subject to strict quotas, and perform poorly on large-scale data. They are not recommended for frequent, high-volume transaction updates. Why are the others incorrect? E. Querying external data sources in cloud storage is significantly slower than querying data stored natively in BigQuery, which violates the requirement to maximize performance.
You are designing a cloud-native historical data processing system to meet the following conditions. The data being analyzed is in CSV, Avro, and PDF formats and will be accessed by multiple analysis tools including Dataproc, BigQuery, and Compute Engine. A batch pipeline moves daily data. Performance is not a factor in the solution. Solution design should maximize availability. How should you design data storage for this solution? The options are: Option A, create a Dataproc cluster with high availability. Store the data in HDFS and perform analysis as needed. Option B, store the data in BigQuery. Access the data using the BigQuery connector on Dataproc and Compute Engine. Option C, store the data in a regional cloud storage bucket. Access the bucket directly using Dataproc, BigQuery, and Compute Engine. Option D, store the data in a multi-regional cloud storage bucket. Access the data directly using Dataproc, BigQuery, and Compute Engine.
To arrive at the correct answer, we focus on the keywords, CSV, Avro, and PDF formats, accessed by multiple analysis tools including Dataproc, BigQuery, and Compute Engine. Performance is not a factor, maximize availability.
The correct answer is option D, store the data in a multi-regional cloud storage bucket. Access the data directly using Dataproc, BigQuery, and Compute Engine.
Why is this correct? D. A multi-regional cloud storage bucket supports multiple formats, including PDF, integrates natively with Dataproc, BigQuery, and Compute Engine, and maximizes availability across regions. Why are the others incorrect? A. Storing data in HDFS on Dataproc is less durable and more expensive for long-term storage than cloud storage, and does not seamlessly integrate with BigQuery. B. BigQuery cannot natively store or process unstructured PDF files, making it an inappropriate storage solution for this mix of formats. C. A regional bucket offers lower availability than a multi-regional bucket. Because maximizing availability is required and performance is not a factor, a multi-regional bucket is the better choice.
You have a petabyte of analytics data and need to design a storage and processing platform for it. You must be able to perform data warehouse-style analytics on the data in Google Cloud and expose the dataset as files for batch analysis tools in other cloud providers. What should you do? The options are: Option A, store and process the entire dataset in BigQuery. Option B, store and process the entire dataset in Bigtable. Option C, store the full dataset in BigQuery and store a compressed copy of the data in a cloud storage bucket. Option D, store the warm data as files in cloud storage and store the active data in BigQuery. Keep this ratio as 80% warm and 20% active.
To arrive at the correct answer, we focus on the keywords: data warehouse style analytics, expose the dataset as files, other cloud providers.
Correct answer is option C, store the full dataset in BigQuery, and store a compressed copy of the data in a cloud storage bucket.
Why is this correct? C. BigQuery handles the data warehouse style analytics efficiently. Storing a compressed copy in cloud storage satisfies the requirement to expose the entire dataset as files for external batch analysis tools. Why are the others incorrect? A. Storing only in BigQuery does not satisfy the requirement to expose the dataset as files for batch analysis tools in other cloud providers. B. Bigtable is designed for low-latency NoSQL workloads, not data warehouse analytics, and it does not expose datasets as files. D. Splitting the data arbitrarily between storage services does not make the full dataset available for both warehouse analytics and file-based batch analysis.
You work for a manufacturing company that sources up to 750 different components, each from a different supplier. You've collected a labeled dataset that has on average 1,000 examples for each unique component. Your team wants to implement an app to help warehouse workers recognize incoming components based on a photo of the component. You want to implement the first working version of this app as proof of concept within a few working days. What should you do? The options are: Option A, use Cloud Vision AutoML with the existing dataset. Option B, use Cloud Vision AutoML, but reduce your dataset twice. Option C, use Cloud Vision API by providing custom labels as recognition hints. Option D, train your own image recognition model leveraging transfer learning techniques.
To arrive at the correct answer, we focus on the keywords: 750 different components, labeled dataset, 1,000 examples for each unique component, recognize incoming components based on a photo, within a few working days.
The correct answer is option A, use Cloud Vision AutoML with the existing dataset.
Why is this correct? A. Cloud Vision AutoML allows training custom image classification models quickly with minimal effort using your existing labeled dataset. This perfectly meets the requirement to build a proof of concept within a few working days. Why are the others incorrect? B. Reducing the dataset size is unnecessary. Cloud Vision AutoML can easily handle 750 classes with 1,000 images each, and reducing data would only lower the resulting model's accuracy. C. The standard Cloud Vision API uses pre-trained models for general objects and cannot be customized to identify your 750 specific proprietary components simply by providing hints. D. Manually training a custom model using transfer learning requires significant machine learning expertise, infrastructure setup, and coding. This approach would take much longer than the required few working days.
You are working on a niche product in the image recognition domain. Your team has developed a model that is dominated by custom C++ TensorFlow ops your team has implemented. These ops are used inside your main training loop and are performing bulky matrix multiplications. It currently takes up to several days to train a model. You want to decrease this time significantly and keep the cost low by using an accelerator on Google Cloud. What should you do? The options are: Option A, use Cloud TPUs without any additional adjustment to your code. Option B, use Cloud TPUs after implementing GPU kernel support for your customs ops. Option C, use Cloud GPUs after implementing GPU kernel support for your customs ops. Option D, stay on CPUs and increase the size of the cluster you're training your model on.
To arrive at the correct answer, we focus on the keywords: custom C++ TensorFlow ops, decrease this time significantly, using an accelerator.
The correct answer is option C, use Cloud GPUs after implementing GPU kernel support for your customs ops.
Why is this correct? C. Implementing GPU kernel support allows your custom C++ ops to execute efficiently on cloud GPUs, providing a significant speedup and utilizing an accelerator cost-effectively. Why are the others incorrect? A. Custom C++ TensorFlow ops require specific kernel support to run on accelerators and cannot be executed on TPUs without additional adjustments. B. Cloud TPUs require TPU-specific implementations, such as XLA custom calls, and cannot execute GPU kernels. D. Scaling CPU clusters is generally less cost-effective for bulky matrix multiplications than using accelerators and ignores the requirement to use an accelerator.
You work on a regression problem in a natural language processing domain, and you have 100M labeled examples in your dataset. You have randomly shuffled your data and split your dataset into train and test samples in a 90 out of 10 ratio. After you trained the neural network and evaluated your model on a test set, you discover that the root mean squared error, RMSE, of your model is twice as high on the trained set as on the test set. How should you improve the performance of your model? The options are: Option A, increase the share of the test sample in the train-test split. Option B, try to collect more data and increase the size of your dataset. Option C, try out regularization techniques, e.g., drop out of batch normalization, to avoid overfitting. Option D, increase the complexity of your model by, e.g., introducing an additional layer or increase sizing the size of vocabularies or n-grams used.
To arrive at the correct answer, we focus on the keywords 100M labeled examples, root mean squared error, RMSE, of your model is twice as high on the train set as on the test set.
The correct answer is option D, increase the complexity of your model by, e.g., introducing an additional layer or increase sizing the size of vocabularies or n-grams used.
Why is this correct? D. A higher error on the training set than the test set indicates underfitting, high bias. With an enormous 100M example dataset, the model lacks the capacity to capture underlying patterns, making increasing model complexity the appropriate solution. Why are the others incorrect? A. Adjusting the train test split will not solve underfitting. A 10% test set of 100M examples is already 10M, providing a very robust and sufficient evaluation sample. B. Adding more data helps with overfitting, not underfitting. Since the dataset is already 100M examples, the bottleneck is model capacity, not data quantity. C. Regularization prevents overfitting by constraining the model. Since the model is already underfitting, high training error, regularization would restrict it further and worsen overall performance.
You use BigQuery as your centralized analytics platform. New data is loaded every day, and an ETL pipeline modifies the original data and prepares it for the final users. This ETL pipeline is regularly modified and can generate errors, but sometimes the errors are detected only after 2 weeks. You need to provide a method to recover from these errors, and your backups should be optimized for storage costs. How should you organize your data in BigQuery and store your backups? The options are: Option A, organize your data in a single table, export and compress and store the BigQuery data in cloud storage. Option B, organize your data in separate tables for each month and export, compress, and store the data in cloud storage. Option C, organize your data in separate tables for each month and duplicate your data on a separate dataset in BigQuery. Option D, organize your data in separate tables for each month and use snapshot decorators to restore the table to a time prior to the corruption.
To arrive at the correct answer, we focus on the keywords, detected only after 2 weeks, recover from these errors, optimized for storage costs.
The correct answer is option B, organize your data in separate tables for each month, and export, compress, and store the data in cloud storage.
Why is this correct? D. Exporting compressed data to cloud storage is the most cost-effective backup strategy. Separate tables allow efficient incremental backups, fulfilling the requirement to recover from errors detected beyond the 7-day time travel window while minimizing storage costs. Why are the others incorrect? A. Maintaining a single table requires exporting the entire dataset daily for backups, which is highly inefficient and drastically increases storage costs compared to exporting smaller, separate tables. C. Duplicating data in a separate BigQuery dataset incurs much higher ongoing storage costs compared to storing compressed, archived backups in cloud storage. D. BigQuery snapshot decorators, time travel, only retain historical data for a maximum of 7 days, which is insufficient for recovering from errors detected after 2 weeks.
The marketing team at your organization provides regular updates of a segment of your customer dataset. The marketing team has given you a CSV with 1 million records that must be updated in BigQuery. When you use the update statement in BigQuery, you receive a quota exceeded error. What should you do? The options are: Option A, reduce the number of records updated each day to stay within the BigQuery update DML statement limit. Option B, increase the BigQuery update DML statement limit in the quota management section of the Google Cloud Platform console. Option C, split the source CSV file into smaller CSV files in cloud storage to reduce the number of BigQuery update DML statements per BigQuery job. Option D, import the new records from the CSV file into a new BigQuery table. Create a BigQuery job that merges the new records with the existing records and writes the results to a new BigQuery table.
To arrive at the correct answer, we focus on the keywords 1 million records, updated in BigQuery, update statement, quoted exceeded error.
The correct answer is option D, import the new records from the CSV file into a new BigQuery table. Create a BigQuery job that merges the new records with the existing records and writes the results to a new BigQuery table.
Why is this correct? D. BigQuery limits the number of DML statements per table per day. The best practice for bulk updates is to load new data into a temporary table and use a single merge statement to update the target table, avoiding quota limits. Why are the others incorrect? A. BigQuery quotas limit the total number of DML statements executed per day, not the number of records updated in a single statement. Reducing records per update won't solve the limit. B. DML statement quotas in BigQuery, such as the maximum number of update operations per table per day, are fixed limits and cannot be increased through the Cloud Console. C. Splitting the file into smaller ones requires executing more individual update statements, which would consume the daily DML quota even faster and worsen the quota exceeded error.
As your organization expands its usage of GCP, many teams have started to create their own projects. Projects are further multiplied to accommodate different stages of deployments and target audiences. Each project requires unique access control configurations. The central IT team needs to have access to all projects. Furthermore, data from cloud storage buckets and BigQuery datasets must be shared for use in other projects in an ad hoc way. You want to simplify access control management by minimizing the number of policies. Which 2 steps should you take? Choose 2. The options are: Option A, use Cloud Deployment Manager to automate access provision. Option B, introduce resource hierarchy to leverage access control policy inheritance. Option C, create distinct groups for various teams, and specify groups in Cloud IAM policies. Option D, only use service accounts when sharing data for cloud storage buckets and BigQuery datasets. Option E, for each cloud storage bucket or BigQuery dataset, decide which projects need access. Find all the active members who have access to these projects, and create a Cloud IAM policy to grant access to all these users.
To arrive at the correct answer, we focus on the keywords: central IT team needs to have access to all projects, simplify access control management, minimizing the number of policies.
The correct answers are Option B, introduce resource hierarchy to leverage access control policy inheritance. And Option C, create distinct groups for various teams, and specify groups in Cloud IAM policies.
Why is this correct? B. GCP resource hierarchy allows policies set at the organization or folder level to be inherited by child projects. This grants the central IT team access to all projects with a single policy, minimizing policy count. C. Using Google Groups simplifies access management by allowing you to update group membership centrally instead of modifying IAM policies across multiple individual resources, reducing policy complexity. Why are the others incorrect? Cloud Deployment Manager can automate infrastructure deployment, but it does not inherently simplify or minimize the number of IAM policies required for access control management. D. Restricting data sharing exclusively to service accounts is impractical for ad hoc sharing involving human users and does not address the need to simplify overall access control management. Why are the others incorrect? Managing individual user access on a per-resource basis creates enormous administrative overhead and maximizes the number of policies, which directly contradicts the goal of minimizing policy count.
Your United States-based company has created an application for assessing and responding to user actions. The primary table's data volume grows by 250,000 records per second. Many third parties use your application's APIs to build the functionality into their own front-end applications. Your application's APIs should comply with the following requirements: single global endpoint, ANSI SQL support, consistent access to the most up-to-date data. What should you do? The options are: Option A, implement BigQuery with no region selected for storage or processing. Option B, implement Cloud Spanner with the leader in North America and read-only replicas in Asia and Europe. Option C, implement Cloud SQL for PostgreSQL with the master in North America and read replicas in Asia and Europe. Option D, implement Bigtable with the primary cluster in North America and secondary clusters in Asia and Europe.
To arrive at the correct answer, we focus on the keywords: United States-based, 250,000 records per second, single global endpoint, ANSI SQL support, consistent access to the most up-to-date data.
The correct answer is option B, implement Cloud Spanner with the leader in North America and read-only replicas in Asia and Europe.
Why is this correct? B. Cloud Spanner provides a single global endpoint, supports ANSI SQL, and offers strong consistency. It easily handles 250,000 writes per second. Having the leader in North America matches the company location for low latency. Why are the others incorrect? A. BigQuery is an analytics data warehouse, not an OLTP database. It is not designed to handle continuous single-row transactions at 250,000 records per second. C. Cloud SQL cannot scale its write throughput to handle 250,000 records per second, as it is limited by single-node capacity. D. Bigtable is a NoSQL database and does not provide ANSI SQL support, violating a core requirement, although it could handle the write volume.